Welcome to the channel, fact lovers. Today we're taking a deep dive into the world of particle physics. You might think physics is all equations on a chalkboard, but it's really about smashing things together to see what they're made of. And what better place to do that than CERN? Now CERN, or the European Organization for Nuclear Research, is home to the Large Hadron Collider, the world's most powerful particle accelerator. Imagine a 17-mile-long racetrack for protons buried deep beneath the Swiss-French border. That's the LHC. In this incredible machine, scientists accelerate particles to nearly the speed of light and then smash them together. It's like throwing a Ferrari at a wall to see what makes it tick, but on a subatomic level. So buckle up, because we're about to unlock some mind-blowing secrets about the universe right here at CERN.
The Large Hadron Collider is a truly awe-inspiring feat of engineering. Picture this: a 27-kilometer ring of superconducting magnets, chilled to a temperature colder than outer space. That's colder than the coldest, darkest nebula you can imagine. These magnets act as an invisible hand, guiding billions of protons around the ring at nearly the speed of light. To give you a sense of scale, these particles complete over 11,000 laps around the LHC every single second. That's faster than a cosmic ray zipping through our galaxy. And it's not just about speed, it's about precision. The beams of protons are focused down to the width of a human hair, ensuring that when they collide, we get the most out of those tiny explosions of energy. The LHC is like a giant microscope, but instead of light, we're using particles to probe the fundamental building blocks of the universe. And trust me, the images we're getting are far more mind-blowing than anything you've ever seen under a microscope.
Now you might be wondering, what's the big deal about smashing particles together? Well, imagine if you could recreate the conditions that existed just a fraction of a second after the Big Bang. That's what the LHC is designed to do. When these protons collide, they release an incredible amount of energy in a tiny space. This energy transforms into new particles, some of which existed only in the universe's earliest moments. It's like a cosmic time machine giving us a glimpse into the universe's infancy. By studying the properties of these particles, we can piece together the fundamental laws of nature. It's like trying to understand the rules of a game by watching how the pieces move on a board. The LHC is not just a tool for discovery, it's a testament to human ingenuity. It's a symbol of our insatiable curiosity and our relentless pursuit of knowledge about the universe and our place within it.
Okay, folks, buckle up because we're diving into the realm of particle physics. You see, in the universe's grand play, every actor, every particle needs its costume, its mass. But for the longest time, we didn't know where this mass came from. It was the universe's best-kept secret. Enter the Higgs boson. Imagine a bustling cosmic party, right? The Higgs boson is like this invisible field permeating the party, interacting with guests, the particles, as they move through. Some particles, like photons, waltz through effortlessly, no mass gained. Others, like quarks, get caught up in the crowd, interacting more strongly, gaining more mass. This, my friends, is how we think mass is born. The 2012 discovery of the Higgs boson at CERN was monumental. It was like finding the final piece of a cosmic jigsaw puzzle, validating decades of theoretical work. This elusive particle, often dubbed the God particle, isn't about religion, folks. It's about understanding the fundamental fabric of reality, the very essence of why things have mass.
We've mapped the stars, galaxies, and even the cosmic microwave background radiation, the faint afterglow of the Big Bang. But there's a cosmic elephant in the room, or rather, a cosmic phantom, dark matter. It's out there, lurking in the shadows, making up a whopping 85% of the matter in the universe. Here's the thing about dark matter. It doesn't emit, absorb, or reflect light. It's invisible to our telescopes. So how do we even know it's there? Through its gravitational influence. We see stars swirling around galaxies faster than they should if all the mass were visible. We see galaxies clustered together in ways that defy our understanding of gravity. Something massive is holding it all together, and that something is, you guessed it, dark matter. Now CERN comes into play. While telescopes are great for observing the luminous universe, the LHC allows us to create conditions so extreme that we might be able to produce and study dark matter particles directly. Think of it as creating a mini-universe, smashing particles together at incredible energies, hoping to see glimpses of this elusive substance. So, we've talked about the Large Hadron Collider, smashing particles together at incredible speeds, pushing the boundaries of what we know. It's like a cosmic billiards game, but instead of pool balls, we're talking about the fundamental building blocks of the universe, the very essence of matter. Now, some of you might be wondering, what about black holes? These mysterious and powerful entities have always fascinated scientists and the public alike. Could the LHC actually create one? This question has sparked much debate and curiosity. Well, it's a fascinating question, and as with all things in science, we have to look at the evidence and the theoretical possibilities. We must approach it with a critical and open mind. Some theoretical physics models suggest that under extreme conditions like those created in the LHC, it might be possible to produce microscopic black holes. These models are based on complex equations and advanced theories. But hold on, don't panic just yet. The reality is far less alarming than it might initially sound. We're talking about quantum black holes here, not the supermassive ones gobbling up stars in distant galaxies. These are entirely different beasts. These hypothetical quantum black holes would be incredibly tiny, almost unimaginably small, existing on a scale that defies our everyday understanding. To give you a sense of scale, imagine a proton, which is already incredibly small. Now, shrink that proton down by another billion times, and you're getting close to the scale of these theoretical black holes. It's a mind-boggling concept, isn't it? They would exist on a scale far smaller than anything we can currently observe with even our most powerful instruments. Our current technology simply isn't capable of detecting such minuscule phenomena, and even if they were created, these quantum black holes would be incredibly short-lived. They would vanish almost as soon as they appeared. According to our current understanding of physics, they would evaporate almost instantly, much faster than the blink of an eye. This rapid evaporation is a key aspect of their theoretical nature. So, while the idea of creating black holes in a lab might sound like something out of science fiction, the reality is far more nuanced and, dare I say, even more fascinating. It's a testament to the incredible complexity and beauty of our universe.
Now, I understand that the idea of creating even microscopic black holes, however theoretical, might give some people pause. It's like that feeling you get when you're standing a little too close to the edge of a skyscraper's observation deck, where the height can make you feel uneasy. But let me assure you, CERN has taken every precaution to ensure the safety of their experiments, leaving no stone unturned. Safety is paramount at CERN, and their scientists and engineers have conducted extensive safety studies, analyzing the potential risks and implications of their experiments with meticulous care. These studies have consistently shown that even if microscopic black holes were produced, they would pose no threat to Earth, dissipating almost instantly. Think about it this way. Cosmic rays, which are high-energy particles from space, constantly bombard our planet with energies far greater than those achieved at the LHC, without causing harm. These cosmic rays have been hitting Earth for billions of years, and we're still here, thriving and pondering the mysteries of the universe, undisturbed by their presence. CERN's safety measures are designed to contain any potential risks within the confines of the LHC, ensuring a controlled environment. The particle beams are circulated and collided within a tightly controlled environment, surrounded by sophisticated detectors and safety systems, constantly monitored by experts. It's like having a state-of-the-art laboratory, buried deep underground, where scientists can safely tinker with the fundamental building blocks of the universe, pushing the boundaries of human knowledge.
Now let's delve a little deeper into the science behind why these hypothetical microscopic black holes wouldn't pose a threat, even if they were created. And to do that, we need to talk about one of the most brilliant minds of our time, Stephen Hawking. Hawking made groundbreaking contributions to our understanding of black holes, and one of his most significant insights was the concept of Hawking radiation. You see, classical physics tells us that nothing, not even light, can escape the gravitational pull of a black hole. But Hawking showed that when you factor in quantum mechanics, things get a little more complex. In the quantum world, empty space isn't actually empty. It's teeming with virtual particles constantly popping in and out of existence. Hawking realized that if these virtual particles popped into existence near the event horizon of a black hole, one particle could be pulled in while the other escapes. This escaping particle carries away a tiny bit of the black hole's energy, and over time this process, known as Hawking radiation, causes the black hole to slowly evaporate. It's like a tiny leak in a cosmic dam, slowly draining away its energy until it disappears entirely. So, we've talked about the theoretical possibility of creating microscopic black holes at the LHC, the Large Hadron Collider. But the real question is, have we actually seen any evidence of these tiny space-time distortions, these minuscule black holes? Well, despite years of intense research and countless particle collisions, the answer so far is no. We haven't found any direct evidence yet. The detectors at the LHC are some of the most sensitive instruments ever built by humans, capable of detecting the faintest of signals. They're designed to pick up even the faintest signals that might hint at the creation of new particles or phenomena, including black holes. And believe me, scientists are meticulously analyzing every bit of data that comes out of these collisions, searching for anything out of the ordinary, any anomaly. But even with this level of precision, we haven't seen any telltale signs of black holes popping into existence, not even a hint. No sudden bursts of Hawking radiation, no unexplained gravitational anomalies, nothing that would indicate the presence of these tiny black holes. Now, that doesn't definitively rule out the possibility. It just means we haven't found them yet. But it does mean that if microscopic black holes are being created, they're even more elusive than we thought, hiding in the data. And you know, that's the beauty of science. It's a continuous journey of discovery. We don't shy away from the unknown, we embrace it. Every null result, every unexpected outcome, every experiment that doesn't confirm our hypotheses is a step forward. It brings us one step closer to understanding the true nature of the universe, unraveling its deepest mysteries.
You know, it's fascinating how the human mind works. We have this incredible capacity for imagination, for envisioning things beyond our immediate reality, and sometimes that imagination can lead us down some pretty interesting paths, especially when it comes to scientific discoveries. Take the LHC, for example. The idea of creating black holes, even microscopic ones, is enough to spark anyone's imagination. It conjures up images from science fiction, of cosmic portals and alternate dimensions, and let's be honest, who doesn't love a good black hole story? But as with any powerful tool, imagination needs to be tempered with reason and understanding. And that's where things can get a bit tricky, because not everyone has the time or the background to delve into the complexities of particle physics. So, it's no surprise that the prospect of creating black holes at CERN has generated its fair share of public concern. We've seen headlines screaming about doomsday scenarios, conspiracy theories running rampant online, and even lawsuits filed in an attempt to halt the experiments.
There you have it, a glimpse into the world of CERN and the incredible science happening at the Large Hadron Collider. We've explored the fundamental building blocks of the universe, delved into the mysteries of dark matter, and even tackled the public's fascination with black holes. And while we may not have all the answers yet, the journey of discovery is just as important as the destination. So keep asking questions, keep exploring, and never lose your sense of wonder. If you enjoyed this journey through the cosmos, make sure to like, subscribe, and hit the bell icon for more mind-expanding adventures. See you next time, fact lovers. And for even more information about CERN and the LHC, visit https://home.cern/about.